Okay, let's get started. So today we will continue our discussion about action and action Lagrangian formalism for E and M fields. So in the previous lecture, we showed that even if we have no knowledge about Maxwell's equation, okay, by just thinking about the symmetry and utilizing the principle of locality, we can already write down the action of E and M field and action how does E and M field couples with matter in a unique way. Okay, so the action of the E and M field, we show that it must take this form. That's the only form that's allowed by symmetry and the principle of locality. And as for the coupling between E and M field and the matter, it has to take this form. Okay? There are only two quantities we cannot decide from the symmetry. One is this coefficient alpha. The other is this coefficient, we call it alpha prime. Okay, which means experimentally, we just need to measure these two numbers. As long as these two numbers, the action of electrodynamics is uniquely determined. Okay? And today we will continue our discussion. As we mentioned earlier on, once we know the action, then we can immediately write down the equation of motion by just taking the variation principle, requesting that the variation of action needs to be zero. Okay, so that is what we are going to do today. Okay? So today we are going to start from the action we obtained the last time. And then we will do a variation of the action and request it equals zero. And that will give us equation of motion for E and M fields. Okay, so as we know that the action is already uniquely determined by symmetry. The only thing we need to do is to measure these two numbers. Okay, and since action is uniquely determined, we know the action, then the equation of motion is also something uniquely determined by symmetry. Okay, we don't need any input from the experiment. We can already write down the equation of motion. And the only thing we need from the experimental side is to measure these two numbers, as we will show later. Okay, so let's start by looking at the action and try to get the equation of motion. Okay, so this is what we are going to do in today's lecture. So today, instead of starting from the E and M field Lagrangian, let's do the action of a generic Lagrangian. Okay, let's say we have a generic Lagrangian, and this Lagrangian describes some field. This field, I will call it phi. This field could be the scalar potential, could be the vector potential, could be something else. It's an arbitrary field we have in our system. Okay. And similar to what we discussed in the previous lecture, for this field, it has a Lagrangian density. Okay, and this Lagrangian density depends on the field and also depends on the space and time derivative of the field. Once we have Lagrangian density, we can do a time and space integral, and that gives us the action. Okay? So generically, for a continuum field, the action always takes this structure. Okay? And for the E and M field, we showed that indeed it takes this structure, as we did in the previous lecture. Okay? So if we have this action, and then we try to get the equation of motion. Okay? To get the equation of motion, we just need to do this. Okay? We request that this action, if we take a small variation of the field phi, and the variation of action need to be zero. Okay, so basically we change the field from phi to phi plus delta phi, where delta phi is some small variation of my field, and then we let this s phi plus delta phi to subtract s phi, subtract our old action, and we require this whole thing to be zero. Okay, for any small delta phi. That's what we do. Okay. And as we showed, similar to the what's that called, classical mechanics, this what gives us the equation of motion. Okay, and in principle, we should go through the derivation and get the equation of motion. But today I will skip that procedure. The reason I will skip that procedure is because this procedure is exactly the same as what we did in classical mechanics, and as we reviewed, in the first section of this chapter. Okay, as we see in the first section of this chapter. In classical mechanics, say we have action of, say, some coordinate q. It depends on coordinate q and time derivative of q dots. Okay. In classical mechanics, if we request this guy equals zero, we showed the earlier part of this chapter. Okay, this variation, if you do this variation calculation, it gives you an equation of motion of this delta Lagrangian delta q equals to delta Lagrangian delta q dot time derivative. Okay, so in classical mechanics, if we do aeration, this is what we have. Okay. Let me massage the right side a little bit. Partial t, that's the same time derivative, delta L, delta partial q, partial t. Okay. So the denominator here is the time derivative of q. I just write down explicitly this denominator is time derivative of q. Okay. So this is what we got in classical mechanics. We already know this very well, and we already showed how to get this in the early part of the lecture. Okay. And now what we're dealing here is field. Okay. So for field, the field phi and the coordinate q in classical mechanics, they are very similar to each other. If you do the variation calculation, they follow exactly the same procedure. The only difference is that for the field, we not only have time derivative, we also have spatial derivative. Okay, so this spatial derivative will give us additional terms in the equation of motion. Those additional terms look exactly like the time derivative, except that that spatial derivative. We replace time derivative by spatial derivative. As a result, eventually what we will see is an equation of motion that looks like this. Okay, as we can see, the left-hand side and the left-hand side of our classical mechanics equation of motion is exactly the same. Okay, in classical mechanics, we have variation of Lagrangian to q. Okay, q is my canonical coordinate. And for continuous field, we have variation of Lagrangian density to the field phi. Okay, so the left-hand side is exactly the same. For the right-hand side, the first term we got here, remember 0 dimension is our time dimension. Okay, the first term that we got here is the same as what we have in classical mechanics. Okay, we have Lagrangian variation of time derivative, Lagrangian variation of time derivative, then another time derivative in front, another time derivative in front. It's the same term. We got this for exactly the same reason. Okay, and what do we get? The extra term here we got. Okay, as you can see here. These guys are exactly the same, has exactly the same structure as the time derivative. Okay, but now we need to do the same thing for x derivative, y derivative, y derivative, z derivative, z derivative. Okay, the reason we have this additional term is because in our Lagrangian, now we have a field phi. So for field phi, we not only have time derivative, we also have x derivative, we also have y derivative, and we also have z derivative. These additional terms give us these additional terms. And all these terms looks exactly as the same as the time derivative term. Okay, so for the time derivative is one time derivative here, one time derivative here. And this second term, you just replace time derivative by spatial derivatives. That's your second term. If you replace the time derivative by the spatial derivative y, you got this term. And z, you got this term. Okay. And if you are interested, you can go through the variation calculation, same as what we did in classical mechanics. And if you go through the calculation, you will see that exactly the only new thing is you get these three new terms. Okay. Now, these three new terms are not really new terms. They are the same term as the time derivative term. Now they appear just because we are dealing with field. So field phi not only depends on time, it also depends on spatial coordinate x, y, z. That's where this three terms comes from. Okay. So the bottom line, if we do the variational principle, request delta s equals 0 and get our equation of motion for continuous field, this is the equation of motion we will get. Okay. The left-hand side is the same as classical mechanics. The right-hand side is a little bit more complicated. Okay. In classical mechanics, we only have the time derivative term. Okay. But in for classical field theory, the right-hand side not only have time derivative, but also have x derivative, y derivative, and z derivative. We repeat the same term 4 times for time, x, y, and z. Okay, and one can also write this 4 derivative together in a more compact form. That's this one. Okay, remember in Einstein, we are using Einstein's convention. We have a derivative of mu here, and we have derivative of mu here. The mu index repeated twice here. And the repeating index means this mu, we need to take this mu on 0, 1, 2, 3, and we add them together. Okay, so this is just a more compact way to write down this sum. Okay, so this is the equation of motion for a generic field, classical field. Okay, the generic classical field will get this equation of motion. Now let's go back to our E and M field. Okay, and then let's apply this equation of motion to our E and M field Lagrangian we derived in the previous lecture. Okay, so in the previous lecture, we showed that the action or the more precise Lagrangian density can be split into 3 parts. The first part is my EMM field part. That part is E squared minus B squared. Okay, that's the only scalar we have, which is invariant under space invariant and time reversal, we showed from last time. Okay, and there is a coupling term that couples my field phi and A with my matter. The matter gives me charge density and current density, and charge density and current density couples with electric magnetic field in this way. And there is an unknown parameter alpha prime. Okay, and finally there is another Lagrangian. This Lagrangian describes the motion of my matter particles or matter. Okay, and right now let's ignore the matter part. Okay? And let's focus on what happens that involves EMM field. The matter part don't involve EMM. The matter part does not contain E or M or phi or A. So right now let's focus on E and B, and phi and A part. Okay. So and then we know the Lagrangian, then we can use this equation to obtain the equation of motion. Okay. Before we do the equation of motion, we need to solve one more puzzle or answer one more question. Okay. So in this Lagrangian density formula, as you can see, we have electric field E, we have magnetic field B, but at the same time, we also have phi, scalar, and A, vector potential. Okay, so the question here is, when we try to get the equation of motion, should we do the variation for E and B field, or should we do the variation for phi and A field? We know E and B field can describe magnetic electric field, and phi and A can also describe electric and magnetic field. There are two type of coordinates we can use in either way to describe E and B field. So which one should we use to do the variation calculation and to get the equation of motion? Okay, that's the question we need to answer first. And the answer is quite obvious. We already mentioned this concept a little bit in an earlier lecture, We should use phi and A instead of E and B. Okay. The reason, I think we already briefly mentioned this in earlier lectures. The reason is because for E and B, they have 6 components in total. 3 components of E, 3 components of B. They have 6 components. Okay, and these 6 components are not independent of each other. Instead, these 6 components, there is some constraint we must follow. For example, the curl of B need to be 0. The curl of B need to be 0. That's a constraint on the 3 coordinates of B field. So the 3 coordinates of B field, Bx, By, Bz are not independent. If I know Bx and By, then I can use this equation to solve for Bz. Bz is already determined. Okay, so this type of constraint means E and B is a bad set of coordinates for variation principle. Okay, similar to the pendulum problem. So remember, in the beginning of this lecture, in the beginning of this chapter, we studied a pendulum problem. Okay, so in the pendulum problem, I mentioned that we can have 2 options for the coordinates. One is to use angle theta. Okay, so this angle, we call this angle theta. This angle theta gives me a coordinate describe motion of this pendulum. Okay, and we can choose another coordinate, which is x and y, coordinate of this this mass point. Okay, so the xy coordinates of this mass point can also be a coordinate we can utilize to describe this pendulum. And the theta angle is much better in terms of variation principle and get the equation of motion. The reason is because xy coordinates are not independent of each other. We need to satisfy the constraint x squared plus y squared equals r squared. R is the length of this pendulum, okay? Because the distance between this mass point and the origin is always fixed to be r. So this xy coordinate is a bad coordinate because we need to have additional constraint. And this additional constraint, if we want to do variation principle with this constraint, we need to use Lagrangian multipliers and introduce additional terms in the Lagrangian. That makes the math much more complicated. At the end of the day, we got exactly the same equation of motion, but if there is a constraint in our coordinate choice, the calculation becomes much more complicated. Here is exactly the same story. We could use E and B, okay? But the problem is if we use E and B, that is a bad choice. We need to follow some constraints. And we need to put this constraint into the Lagrangian as using the technique of Lagrangian multipliers. Then it makes everything a lot more complicated. At the end of the day, we could get the same result, but the pathway is much more complicated. Okay, so instead, we should choose phi and A. Okay, so once we have phi and A, we don't need to worry about this type of constraint anymore. This type of constraint is automatically satisfied if we use scalar and vector potential. So phi and A are independent coordinates. That's much better than E and B. in terms of variation principles. Okay, so that's why we need to use phi and a. We can't do this with E and B. Okay, so that part is solved. We need to use phi and a. Okay, so in order to use phi and a to do the calculation, the first step is we need to replace this E and B by phi and a. Okay, that's we know how to do. This is because we know B field is curl of curl of A, and the E field is time derivative of A minus the scalar potential gradient. Okay, so we replace this E by this guy, and we replace this B by this guy. Okay. Once we do that, now my Lagrangian is much nicer. It's the same Lagrangian. I replace E with this derivative of phi and A. I replace the B with curl of A. Okay. So now it's the same Lagrangian, but now everything is in terms of A and phi. Everything is in terms of A and phi. We only have A and phi. There's two sets of field. Okay, A has 3 components, x, y, z. Phi has 1 component. It's because it's scalar. It's a 3D scalar. So this field in total we have 4 fields here: phi, ax, ay, and az. Okay, we have 4 fields here, and Lagrangian looks like this. Okay. So now we have Lagrangian. We have our A and phi. Everything is ready. We just need to do the variation principle and get the equation of motion. And the equation of motion is just this guy. Okay. And we just need to do a derivative for the field and then a derivative of the field, and then make them equal to each other, like what we did. Okay. So first, let's do the derivative for the let's do the variation for the scalar field phi. Okay. So for the scalar field, we utilize this equation. Okay. We replace this phi by my scalar field, curly phi. Okay. It's the same equation as we showed earlier on in the previous page. But here, the field, I choose it to be my scalar field, scalar potential phi. Okay, okay. So that's my equation of motion when we do the variation for scalar field phi. So let's write down every single term of this equation of motion and see what it looks like. The first term, let's start from the left-hand side. The left-hand side is the Lagrangian density derivative of phi. Okay, and if we look at the Lagrangian density here, this term is a gradient of phi, it's not phi. This term don't contain phi. The only term contains phi is this guy. Okay? Other term either don't have phi or it has gradients of phi, it's not phi. Okay? If we want to do variation of Lagrangian density to phi, this is the only term that contains phi. If we do the variation, if we take a derivative of phi, we get minus alpha prime rho. So this variation is minus alpha prime rho. Alpha is a parameter, the value is unknown, we need to experiment to determine that, and rho is my charge density. The left-hand side is extremely simple, just an unknown parameter, which need experiment to measure, times charge density. It's the left-hand side. Okay. Now, right-hand side contains 4 terms. Okay. Let's first do the variation. Okay, so let's first look at this term, this time derivative term. So what is the variation of Lagrangian density to the time derivative of scalar field? Okay. If we look at this Lagrangian density, we find that we have spatial derivative phi, and we have phi with no derivative, but there's no time derivative of phi. Okay? There's no partial t phi in my Lagrangian density, which is very good. It means that this variation, Lagrangian density to the time derivative of phi is just 0. Because it does not depend on time derivative of phi. There's no time derivative phi. If we try to take a derivative, it's 0. Okay? So this derivative is 0. How about this variation? Okay? This variation is a Lagrangian density variation of spatial x derivative of phi. Okay? Which term contains spatial derivative x of phi? Okay? This term don't contain any derivative of phi. This term contains phi, but it does not have spatial derivative. The only partial x phi term comes from here, the gradient of phi. Okay? By the way, we can write this vector formula in terms of components. That's this one, okay, if you want to expand it. Okay. Anyway, so we are doing the delta Lagrangian density to the x gradient of phi. The only x gradient, x derivative of phi terms comes from this guy. Okay, so we need to do the derivative of Lagrangian density to this guy, to the partial x phi. This basically means we need to do the derivative of this guy to partial x phi. Okay. And that derivative is this one. It's twice the alpha multiplied by this. Okay, so this is basically the same as saying if you have a function alpha x squared, you want to take the derivative of x, you got 2 alpha x. Okay, that's exactly the same story. Okay. And for this guy, if you pull the common factor 2 alpha out, if you can pull the common factor 2 alpha out, we have a time derivative of a plus the gradient of phi. And the partial t a plus gradient phi by definition is minus ex. That's the definition of ex from this formula. Okay, we have time derivative of a and spatial derivative of phi, add them together, that's minus e. Okay. So this guy combined together is minus 2 alpha times ex. This x component of the electric field. Okay. That's this variation. And we can do the same for this variation. Okay, so this variation is very similar to the first variation we calculated. Just replace x with y. Okay, and the answer is also very similar to the previous term. You just replace x with y. That's this guy. Okay, and the last term, the variation for the z gradient of phi. Again, we got the same structure and through the same calculation, get the same structure. The only difference is now it's a z component of e. Okay, so we got this derivative, this derivative, this derivative, and this derivative figured out. Okay, so now we can write down what happens, what is the right hand side. Okay. The right hand side should contain these 4 terms. The first term, this variation is 0, as we mentioned earlier. Okay, so this guy is 0. So the first term is time derivative of 0. Time derivative of 0 is just 0. Okay. The first term is just 0, nothing. The second term is the partial x derivative of this thing. Okay, and this thing we know is minus 2 alpha ex. So we plug in what we learned here into this term, replace this guy by minus 2 alpha ex. So this whole thing is just the spatial gradient, x gradient of 2 alpha ex with a minus sign. Similarly, this guy is a y gradient, y derivative of minus 2 alpha ey. Okay, the last guy is a z derivative of minus 2 alpha ez. That's what happened on the right hand side. Okay, the right hand side contains this 4 term. The first guy is 0. The rest 3, we know what they are. And then we can massage the formula a little bit. Let's pull a common factor minus 2 alpha out. And then the rest term is partial x ex, partial y ey, plus partial z ez. And partial x ex plus partial y ey plus partial z ez is nothing but the divergence of E. That's the definition of divergence of vector field. Okay. So at the end of the day, we find that the right-hand side is just the minus 2 alpha divergence of E. The right-hand side is minus 2 alpha divergence of E. The left-hand side we already figured out. It's minus alpha prime times charge density rho. So it's minus alpha prime times charge density rho. Okay. And we write down the left side equals right-hand side. This is our equation of motion. Okay. And we can massage the formula a little bit, divided 2 alpha to the other side. Then this is what we got at the end of the day. Okay. We find that what we get at the end of the day is the divergence of E equals to some constant. And this constant value we don't know. We cannot decide the value of this constant from theory and symmetry, but we know it's a constant. It's a physical constant. And then multiplied by charge density. Okay. And what is this equation? This equation is exactly one of the Maxwell's equation. And more precisely, this is Gauss' law. Okay. Gauss told us the spatial gradient, the spatial divergence of E field is charge density divided by epsilon 0. Charge density multiplied by some constant. Okay. From the symmetry, we can see that this has to be true. We don't know what is this value of this coefficient, but divergence of E must be proportional to the charge density. Okay. So in other words, we pretend we didn't know anything about Maxwell's equation from the beginning. Okay. We only utilize the symmetry and the principle of locality, and then we find that Gauss' law is not accident. It has to be true. And the only thing we are not so sure, or we cannot determine from the theory side, is what is the value of this coefficient. Or in other words, what is the value of epsilon 0? And this value of epsilon 0 is something we need to determine experimentally. Once experimentally we measure the value of epsilon 0, then the equation of motion, this equation of motion for E, we know it for sure, it must be this one. Okay. Okay, so basically by comparing with the Gauss law, we find that this ratio alpha prime over 2 alpha, alpha prime over 2 alpha is nothing but the inverse of epsilon, the inverse of the vacuum dielectric constant. Okay, let me emphasize this again. The bottom line, what we proved here, is that electric field has to obey Gauss' law. Okay, and as long as the symmetry argument, like the gauge symmetry, the spatial rotation symmetry, Lorentz boost symmetry, etc., is satisfied, then the physics law for E field has to be the Gauss law. Okay? And the only thing we cannot determine from the symmetry is the value of this coefficient, and that is something we can never expand it, or we need to never expand it. Okay, so that's the equation of motion for the scalar field phi. Now let's do the same thing for the vector potential A. Okay, so in addition to scalar field phi, our action also contains A, and AX, AY, AZ, which means we need to get the same equation of motion for AX, same equation of motion for AY, same equation of motion for AZ. Okay, so we do the variation not only for phi, but also the variation for AX, AY, and AZ. If we do a variation for AX, this will be the equation of motion we got. Okay? It's the same equation of motion as we showed earlier, except that now the field we are looking at is AX, the X component of the vector potential. Okay, and this is our equation of motion. Okay, and let's again start from the left-hand side. Left-hand side is a variation or derivative of Lagrangian density to AX. Okay, let's go back to the Lagrangian density. So this is our Lagrangian density. Which term contains AX? Well, this guy contains AX, but it's not AX, it's a time derivative of AX. This guy contains AX, but again, it's not AX, it's a spatial derivative of AX. There is only one term contains AX, that's this guy. Okay, this guy J dot A contains JX, AX. That's the only AX term we have in the Lagrangian density. Because this is the only term we have that contains AX when we take the variation, take the derivative of Lagrangian density to AX, we got only one term. That's minus alpha prime times minus JX. Okay. Minus sign cancel, it's alpha prime JX. Okay. So this variation from the left-hand side is extremely simple. It's just alpha prime, this unknown parameter, or this parameter that's whose value is unknown, times JX. That's the left-hand side. Extremely straightforward and simple. Okay, so for the right-hand side, okay, for the right-hand side, again, let's look at these four terms, one by another, one after another. Okay. Let's start from this first term. Okay, in the first term, we want to calculate the variation of Lagrangian density to the time derivative of AX. Okay, so Lagrangian density to the time derivative of AX, and then again we go back to the Lagrangian density, and we ask, which term contains time derivative of AX? Okay, the time derivative of AX, it only appears in this term. Okay. The time A time derivative. This guy contains time derivative of AX. So we just need to do a variation for this term. Okay, and I will skip the detailed mathematical procedure. And after you do this variation, you get a very simple term. Okay, it is 2 alpha times time derivative of AX and plus spatial derivative X derivative of phi. And again, this time derivative A, spatial derivative of phi combined together is minus EX. Okay. So this term is just minus 2 alpha EX. Okay. That's the first term. Very easy. So it's minus 2 alpha EX. And the second term has a partial X AX. Okay. Let's go back to the Lagrangian density. Which term has partial X AX? This guy don't. This guy is a time derivative of AX. It does not contain partial X AX. This guy don't. There's no partial derivative. This guy has spatial derivative and A, but it does not have partial X AX because it's a curve. Okay. So for curve, we know that the derivative is cross product. For cross product, we know that the vector on the left-hand side and the vector on the right-hand side need to be orthogonal to each other. They cannot be both along X. Okay, X and X, if you do a curve, it gives you 0. Okay, so this curve do not have partial X AX. Another way to see this is, we write down all the components here, and we can see we have partial X AY, or we have partial Z AX, but there is no partial X AX. The curve don't contain partial X AX. So there's no partial X AX in the Lagrangian density. If there are no partial x, ax in the Lagrangian density, then the gradient or the variation, Lagrangian density to partial x, ax is 0. There is no ax, partial x, ax is 0. And partial y, ay, and partial z, partial y, ax, and partial z, ax, we do have those terms in our Lagrangian density. Say partial y, ax is here, partial z, ax is here. So we do need to take a derivative for those terms, and that gives us these two terms. Okay, we can massage these two terms a little bit, and this guy is actually the z component of magnetic field B, and this guy is actually the y component of magnetic field B. Okay. So that's the 4 terms on the right-hand side. Okay, now we are ready to write down the equation of motion. Left-hand side is variation of L to AX. L to AX, that's alpha prime times JX times current density. Okay, so the left-hand side is alpha prime, with parameters in our theory, times JX. Oh, by the way, JX is current density along the x direction. Okay, and then for the right-hand side, we have these 4 terms. The second term is 0 because the variation is 0. So the time x derivative of variation is 0. The first term is time derivative of this term. And this term itself is minus 2 alpha ex. So the first term is just time derivative of ex times minus 2 alpha. Okay. And this term, we know it's this guy, we plug in its value here. This variation, we know it's this guy, we plug in its value here. Then we can write down the right-hand side of the equation motion. That's what we have here. The left side of the equation motion, right-hand side of the equation motion. Okay. So this is our equation motion for AX. And we can massage this formula a little bit better. Okay, so let's move the E and the J to one side and keep the magnetic field terms to the other side of the equation. Okay, I keep the magnetic field term to one side of the equation and move E and the J to the other side. And I also divided 2 alpha on both sides of the equation, so my magnetic field derivative terms don't have coefficient anymore. Okay, so this term, this partial y bz minus partial z by is nothing but the curl of B with the x component of curl of B, x component of curl of B. Okay, that's this term. Okay, and the other 2 terms, E and the J term, is just this 2. Okay, we move this E to the other side and divide it by every term by 12. This is what we have. Okay. So that's the equation of motion for AX. And we can do the, I forgot to mention one more thing. In the first equation of motion for the Gauss law, we already learned that alpha prime divided by 2 alpha is 1 over epsilon 0. Okay, so we know that alpha prime over 2 alpha is nothing but 1 over epsilon 0 from the Gauss law and the previous equation of motion for phi. So let's replace this ratio by 1 over epsilon 0. Okay. If we replace this by 1 over epsilon 0, and remember, c squared is 1 over c squared, is epsilon 0 times mu 0. Okay. So this guy is epsilon 0 times mu 0, 1 over c squared. This guy is 1 over epsilon 0. When we multiply them together, epsilon 0 cancels, we have mu 0. Okay. So this coefficient is nothing but mu 0. And this coefficient, 1 over c squared, is nothing but epsilon 0 mu 0. Okay. So the equation of motion for AX, variation for AX, eventually is this guy. Okay. That's what we have. And we can repeat the same thing for AY and AZ. Okay. If we repeat the same thing for AY and AZ, we got the same equation except the X components, X component now becomes Y, Y, Y. And all becomes Z, Z, Z. So that's the same equation for Y component and Z component. Okay. So we can combine these 3 equations together as a vector formalism. That's a curl of B equals to mu 0 times the current density plus epsilon 0 mu 0 times time derivative of electric field. Okay. And this equation is one of the key equations in Maxwell's theory. Okay. So we showed that by taking variational principles, we get 2 equations. And that's 2 equations. And these 2 equations are precisely the equation in the Maxwell theory. Okay. And remember, in the Maxwell theory, there are 2 more equations. This guy and this guy. Okay? Maxwell's equation has 4. We recovered 2. Okay, and there are 2 more. Those 2 equations are not really equations. They are actually constraints. Okay, as we showed early on, by requesting those 2 equations actually tells us we can define vector field, vector potential, and scalar potential. Once we define vector potential and scalar potential, as we did here in the Lagrangian density, once we define A and phi, and this last 2 equations automatically satisfy. Okay? Once we know B is a curl of a quantity, then immediately the divergence of B is 0. And once we say E is time derivative of A and the spatial gradient of phi, then the curl of E must equal to this guy. Okay? These 2 equations are not really equations of motion. As long as we know that phi and as long as we define phi and A, they are automatically satisfied. Okay? So from the Lagrangian and the vibration principles point of view, these 2 equations of Maxwell's equations are equations of motion. The other 2 are not really equations of motion. This is a natural consequence of phi and A. Okay? Because we are using phi and A, we are using these good coordinates. This coordinate already tells us we have to obey this constraint for E and B field. These are constraints of E and B field. Okay? And that is the reason why the 4 Maxwell theory equations are different. These 2 contains matter field. Okay? These 2 actually are the real equation of motion. It tells us if you have matter charged particles or charged currents, how does it change E and B? The other 2 equations of Maxwell, you don't have any charge. It does not have charge density. It does not depend on charge density. It does not depend on current. Okay? So these 2 equations, the reason they don't contain charge is because they are not really equation motions. They are not from vibration principle. These 2 equations just described, that tells us E and B fields are not independent. The 6 components, 3 components of E, 3 components of B, are not free coordinates you can choose. Okay? Instead, they obey some constraints, and that's a constraint E and B field has to hold. Okay? And that constraint is automatically taken care of when we define the vector and the scalar potential. Okay? So the 4 Maxwell's equation, 2 of them are really equations of motions, and those 2 depends on charge density and current density. The 2 other ones, they are not really equations of motion. They are constraints E and B field must follow. Because they are constrained E and B field must follow, they don't contain charge current, charge density. They don't contain about the charge particles. They have nothing related with charge particles. Okay, sorry, I think I just realized I have one typo in my previous part of the equation. Oh, sorry, yeah, this one here. So early on, I said the curl of B should equal 0. That's constraint. That was wrong. Actually, it should be the divergence of B equals 0. That is a constraint we need to follow for the B field. Sorry for that. So this was a typo. I will fix this before I post this lecture notes. Okay. Anyway, so by using the vibration principle, we showed that we recovered the Maxwell's theory. Okay. So let me summarize and emphasize again. Okay. So in this chapter, as I mentioned earlier, we assume we don't know about Maxwell's theory at all. Okay? We just asked the following question. The question we asked in this chapter is, suppose we know the symmetries we have to obey in our universe. The symmetries include Lorentz boost. Okay? That's a principle of relativity. All reference frames to see the same physics law. That's one fundamental assumption. And we also have the assumption of the universe is homogeneous and isotropic. Homogeneous means here in this part of the universe and in that part of the universe, we follow the same physics law. And isotropic means I can choose my coordinate x, y, z in any directions. We should get the same physics law, no matter which direction I'll call x or y or z. Okay? And we also have the translation symmetry along time, which means if I do the experiment today and I do experiments tomorrow, or like 100 years later, we should see the same physics law. Okay? So those symmetry constraints tells us, and also the gauge symmetry. We request that phi and A, if we do a gauge transformation, we get exactly the same physics because they give the same E and B fields. Okay? With those assumptions, we find that the equations of motion we need to follow for the electric and the magnetic field is these 4 equations. That's precisely what Maxwell found in Maxwell's theory. Okay? So in this sense, Maxwell's theory is not an accident. It's not something that we accidentally discovered our universe follow Maxwell theory. This Maxwell theory is almost has to be true. Okay, as long as the universe has this symmetry principle, and as long as E and B field is a gauge field, which allows you to do this gauge transformation, and everything still remains the same, then this has to be the equation of motion for this field. Okay, the only thing we cannot say for sure is the parameter in our theory. The two parameters, alpha and alpha prime. Okay, those two parameters need experimental measurements. Actually, more precisely, three parameters: the alpha prime and also speed of light. Those three parameters need experimental measurement. Okay, and once we experimentally measure those quantities, the theory is uniquely determined. Okay, so let me give a small example to demonstrate how powerful this is. So suppose one day we discovered another universe. Okay. And in another universe, the physics law is very different from our universe. But it happens that we know that universe has the same symmetry as our universe. Okay? They have the same spatial translational symmetry and is isotropic. And there is some like a different reference frame has the same physics law, etc. And we know E and B field are gauge field. And so they need to preserve the gauge symmetry. The gauge transformation do not change any physics in that universe. Okay. Then we need to figure out the fundamental physics law in that universe. Okay. So for that universe, because they have the same symmetry as us, we can say immediately their E and M field should obey the same equation as our universe. Every single equation has to be exactly the same. There's no freedom to choose to change any part of the equation. And the only part we may modify or we don't know about that universe is the value of epsilon 0 or mu 0. So what is the value of epsilon 0 in that universe? We don't know. What is the value of mu 0 in that universe? We don't know. We need experiments to measure those quantities. But that is the only input we need to understand E and M theory in that universe. Okay. So this is the reason why this action approach is such a powerful approach. So this approach is a very powerful approach. It's extremely useful for the explorer of unknown. Okay. If we have a system, we have a new system, no matter it's particle physics system or condensed matter system or any system, as long as it can be written in terms of action and variation principles, even if we don't know the detail about the system, we can already say a lot of things about the system. We can already say a lot of things about the equation of motion. Okay? By just following the symmetry, we can write down the structure of the action with some unknown parameters, okay? And let experimentalists to measure those unknown parameters. Then once this unknown parameters is measured, we can get down the equation of motion immediately. Okay? And everything about the equation of motion and all the physics laws is known. Okay? That's the power of why this approach is so useful. Okay, so that is the equation of motion. Okay. So now let's look at the coefficients a little bit more. Okay, as I mentioned to you earlier on, this coefficient alpha and alpha prime and the speed of light, we need experiments to determine these coefficients. Experiment to determine these coefficients. Okay, and now let's look at these three coefficients a little bit more. Okay, first of all, we know from the previous section, 2 alpha over alpha prime is epsilon 0. It's a dielectric constant of the vacuum. Okay? This comes from comparing our equation of motion from vibration principle with the equation of motion in Maxwell's theory, or more precisely the Gauss law. The Gauss law tells us this guy is epsilon 0, so 2 alpha over alpha prime must be epsilon 0. So that's what we learned. Okay? So we know that 2 alpha over alpha prime is epsilon 0. Okay? So in other words, this alpha and alpha prime are not independent parameters. They are related by this formula. Okay? So let's define, or let's replace alpha. So we can replace alpha with alpha prime times epsilon 0 over 2. Okay? So we can treat alpha as the unknown and solve this equation to get alpha. Okay? So we find alpha is nothing but alpha prime times dielectric constant epsilon 0 divided by 2. Okay? So this coefficient alpha, we can replace it with alpha prime epsilon 0 over 2. Let's do that. Okay? So we replace the first coefficient by this guy. And these two quantities have to be equal to each other because we know this equation. Okay? It has to be the same. Okay, now I have alpha prime here and also alpha prime here. I have alpha prime for both terms in my Lagrangian density. Let me pull the common factor out. Okay, so I can rewrite this Lagrangian density with alpha prime multiplied by this constant. Okay. So in this whole thing inside the square bracket, all the parameters known. Okay, speed of light, I know it. Epsilon 0, I know it. Okay. The only unknown parameter is this alpha prime. So what number should I give? What value should I give to this alpha prime? Okay. So in the previous section, we determined the ratio between alpha and alpha prime is epsilon 0. Okay, but we didn't really give a value for alpha and alpha prime. We know their ratio has to be epsilon 0. So what value should alpha prime take? Okay? If I know the value of alpha prime, I can use this equation to get the value of alpha. Okay? So the value of alpha and alpha prime, we didn't actually get the answer in the previous section. The previous section only tells us the ratio is epsilon 0. Okay? So what's the value of alpha prime I should do? I should choose, I should use. Okay? It turns out for the equations of motion, as far as the equations of motion is concerned, this value of alpha prime doesn't matter at all. Okay, you can put any value here as long as it's not 0. You can put any value to the alpha prime, then you get exactly the same equation of motion. The reason is because the equation of motion is a linear function of L. Okay, if I multiply this L Lagrangian density by a constant, say alpha prime, I multiply every single term by the same constant alpha prime, and then this alpha prime will cancel. All the terms are multiplied by alpha prime, so I can cancel them. So multiplying Lagrangian density by a constant does not change the equation of motion. It gives you the same equation of motion. So multiplying Lagrangian density by a constant is multiplying every single term by a constant and by the same constant. Of course, they cancel. So for the equation of motion, you get the same equation. Okay. So in that sense, the overall factor in Lagrangian density does not matter at all. No matter what value you put here, you get the same equation of motion. Right? So whatever value you put here, you give the same contribution for this four terms. You give the same full factor for this four terms as a cancel. So you all give the same equation of motion. Okay? So in that sense, the value of alpha prime does not matter at all. Okay? They all give the same equation of motion. Since all the value of, any value of alpha prime give the same equation of motion, well, why don't we just set it to be 1? That's the simplest choice, right? Okay? So alpha prime equals 1. We can set alpha prime equals 1, then we get the equation of motion. Okay? If we don't set alpha prime equals 1, we set it say equals 2 or pi or square root of 2. Eventually, we get the same equation of motion. This factor all cancels out. Okay? So the natural choice is to set alpha prime equals 1. Okay? If we set alpha prime equals 1, the Lagrangian density will look like this. Okay? It's the same formula as we have above here, but now we don't have alpha prime anymore. It's just 1. Okay? So this is the Lagrangian density we utilize in ENMC. Okay? ENMC. And early on, we showed that there are 3 unknown parameters in this series: speed of light, alpha, and alpha prime. Speed of light really need experiment to know. Ratio of alpha and alpha prime need experiment to know. That's our dielectric constant. But the value of alpha prime itself has no physical meaning. We don't need experiment to know it. We can just choose it to be any parameter, and we will give the same equation of motion. So let's just choose alpha prime equals 1. That's the Lagrangian density we use. Okay. If this is Lagrangian density we use, then for action is just the space-time integral of Lagrangian density. This is action we should use in ENMC. Okay. So in Jackson's book, you will find exactly the same action. Oh, I forgot to mention. In Jackson's book, in this section, Jackson's book mostly using the Gauss unit. And we are using the international unit, same as 505. So in Jackson's book, in this chapter, for some reason, Jackson chose to use Gauss theory, Gauss units. Okay? So the formula may look a little bit different, but at the fundamental level, they are the same function. Okay? So this is the action of the ENM field. So in Jackson's book, basically, the Jackson's book starts from this action and using vibration principle to show it recovers the Lagrangian density. But we know from our lecture, starting from this action, there is a reason behind it. Okay, this action is pretty much the only possible action for ENM field. And then if we use vibration principles, we get maximum theory. Okay, so this is an action you will find in textbooks or in literature. When people discuss about action of ENM field, this is action people are talking about. Okay? And this is a coupling between E and M field is charge density and current density. Okay, so that's about the alpha prime, value of alpha prime, and the full structure of the action. To conclude this part of discussion, I want to say a little bit more about this coefficient alpha prime. Okay. So in the previous section, in this section, I just told you the value of this alpha prime does not matter. Any value I choose for alpha prime, we get the same equation motion. Okay. However, that's not entirely true. Okay. There is a small twist here. For equation of motion, the value of alpha prime does not matter at all. Okay, equation of motion don't care the value of alpha prime. But for the definition of energy, the definition of energy will choose or will pick a specific value for alpha prime. It happens the definition of energy pick this value to be 1. Okay, so let me explain this physics a little bit more in the next section. Okay, so we'll consider the coefficients a little bit more, and this time we will look at the reason why alpha prime is 1 from energy, let's say Hamiltonian. Okay, so before we discuss about energy and Hamiltonian, let me give a very quick and brief review about what is a Hamiltonian. Okay, in classical mechanics, we learned that if we know the Lagrangian of a system, then we can use the Lorentz transformation to get the Hamiltonian of the system. Okay, so Lagrangian depends on, say, coordinates q and the time derivative of q. Okay, so to define Hamiltonian, the first thing we need to do is we need to define the so-called canonical momentum. Okay, so for every canonical coordinate, one can define a corresponding canonical momentum by doing this variation. Okay, so for every coordinate qi, we can do a variation of Lagrangian to time derivative of qi. This derivative or this variation is called the momentum of I. This pi is the corresponding momentum of qi. For every coordinate qi, we can do this derivative and get corresponding momentum. Okay, that's called canonical momentum. Once we have canonical momentum, we can use canonical momentum multiplied by dq dt. Okay, then minus Lagrangian, and that gives us a Hamiltonian. Okay. So if we know Lagrangian, we can use this derivative to define momentum, canonical momentum. And once we have canonical momentum, we can use this formula to define a quantity which we call Hamiltonian. Okay, and in classical mechanics, we know this Hamiltonian is nothing but energy. Okay, so this is a way to define energy in classical mechanics or classical mechanics. Okay, and for the classical field theory or for E and M field theory, we can do the same thing. Okay, so in the field theory, we have our field phi, scalar potential, ax, ay, az, vector potential. And we can first find the momentum, the corresponding canonical momentum for each field. Okay? So for the phi, for scalar field, the definition of a canonical momentum of phi is the same as classical mechanics. We do a Lagrangian density and take a derivative to time derivative of phi. Okay? That's the same as what we did in classical mechanics. And this variation is the canonical momentum of phi. And we can do the same thing for ax, Lagrangian density, and do the derivative of partial t ax. That's so partial t ax and do this variation. That's a canonical momentum of ax. If we do this for, this should be ay. This is a typo. If we do the time derivative of ay and do this variation, this is canonical momentum of ay and canonical momentum of az. Okay. So here, let me emphasize one small, one conceptual, one important concept, and let me highlight one important concept and one important fact. Canonical momentum are not a momentum. Okay? It's not the momentum of an object. It's different. Okay, we will study momentum of E and M field later. So these are the canonical momentum of E and M field. It's not yet momentum. It's not different from the physical momentum. That is the same story is true in classical mechanics. In classical mechanics, pi is a corresponding momentum of qi. It's a canonical momentum of qi. It's not the momentum of the object. Momentum of the object is something different. Okay. So anyway, we can use the same way to define canonical momentum for my phi field, for my ax field, ay field, and az field. Okay. And this variation, we already calculated that in the previous section. So we can copy the same formula. Okay. the Lagrangian density variation for time derivative of phi is 0. That's something we showed in the previous section. Okay, which means the phi field don't have a canonical momentum. Let's say the phi field, the corresponding canonical momentum is always 0. Okay, phi field momentum is always 0. For AX, the corresponding momentum is this variation, and we showed early on this variation gives me alpha EX. Also, sorry, minus 2 alpha EX. Okay, and we will replace alpha with alpha prime, okay, utilizing this formula. Okay. Use this formula. We will replace alpha with alpha prime times epsilon 0 divided by 2. Okay. So the variation gives me alpha. I replace alpha with alpha prime epsilon 0 over 2. So we get this. And for the AY and AZ, we do the same thing. And this is the corresponding canonical momentum of AX, AY, and AZ. Okay, so we call this PAX, PAY, PAZ to mark this as the corresponding canonical momentums. Once we have canonical momentums, we can do the same Lorentz transformation. Okay, so Lorentz transformation tells me I should do momentum times the corresponding time derivative of my object, and momentum times time derivative of my object AX, momentum of AY times time derivative of AY, momentum of AZ times time derivative of AZ minus Lagrangian density. Okay, that's the same Lorentz transformation we have in classical mechanics, exactly the same transformation. Okay. And if we really write this down, for P phi, PAX, PAY, PAZ, we know what are Z. We plug in these values into here. And for Lagrangian, we also know what Lagrangian is. Here, we will focus on the Lagrangian of E and M field, E and B field. I will throw away the matter part and the coupling part. Okay. We'll focus on the E and M field part. Okay. And we know this first 4 terms, and we know this Lagrangian density, so we just write them out. Okay. And yeah, this is what we have. This is the Hamiltonian density. Okay. So we don't, this is not Hamiltonian, it's Hamiltonian density. It's Hamiltonian per volume on this spot. Okay. Similar to the Lagrangian density. It's Lagrangian per volume on this point. This side is Hamiltonian density. It's Hamiltonian per volume on this point. Okay. And this is what we have for the Hamiltonian density. And here we utilize this equation. We have time derivative of AX. Okay. And time derivative of AX, time derivative of AX, AY, AZ. Time derivative of A, we can use this equation. This equation tells us the time derivative of A is nothing but the spatial gradient of phi minus E. Okay, so time derivative of AX is minus partial x phi minus EX. AY is partial y phi minus EY, etc. So we can replace this time derivative of x using this, replace this time derivative of y using this same formula. Okay. And so each time derivative of x now becomes 2 terms, the spatial gradient of phi and the electric field E. So each partial TA becomes 2 terms. That means this term will now split into 2. Okay, so I replace this partial A with this, and then this term split into 2. The first term is nothing but EX squared, EY squared, EZ squared. Okay, the second term is a little bit more complicated. It's EX partial x phi, EY partial y phi, EZ partial z phi. Okay, these 3 terms become these 6 terms. And I copied down my Lagrangian density. My Lagrangian density is still 0. I didn't change that. Okay, and then let's massage this formula a little bit. The first term is easy. EX squared, EY squared, EZ squared is nothing but E squared. It's amplitude of electric field squared. Okay. The second term is also quite easy. This is nothing but E dot the gradient of phi. E dot gradient of phi. Okay. So the second term is just E dot gradient of phi. And last term, Lagrangian density, I still have minus Lagrangian density. I still keep it. Okay. Okay. And as you notice that we have E squared term here. We have E squared term here. We can combine these 2 E squared terms. Okay. This one has a plus sign. This one has a minus sign. This one has coefficient 1. This one has coefficient 1/2. So what we have here is 1 minus 1/2, which equals plus 1/2 E squared. Okay. So this term and this term combined together is plus, oh, sorry, I have a typo here. The alpha prime, I forgot. The alpha prime here is alpha prime here. Our revised selection was before I posted. I missed the alpha prime term here, alpha prime here. So these two terms combined together is alpha prime epsilon 0 over 2 e squared. Okay. And this b term, you have one minus sign here, another minus sign here. These two minus sign combined together become plus sign. That's where this plus sign comes from. And finally, we have this term. I will leave this term at the end. That's my third term. Okay. So bottom line, the Hamiltonian density contains three terms. Oh, sorry, there is one more. So the first two terms, I copied the first two terms. For the last term, I will massage this term a little bit. Okay. So what I will utilize is this. Okay. I will consider a space where there's E field and there's B field in this space. Okay. But there's no charge. Okay. The reason I want this setup is because I want to look at the energy of E and B field. As we learned in 505, E and B field carry energy and also carry momentum. I want to know how much energy does E and B field carry. Okay? So to know how much energy does E and B field carry, I want a space with only E and B field but no matter. Okay? If there is matter, then I can't tell whether this energy is carried by matter or E and B field. I want a setup where my electric charge and electric currents all live somewhere far away. Okay, live somewhere far away. And the field they generate is in this area I'm looking at. And I'm looking at the energy of this area. Okay? So I'm looking at the area where there is field, but there is no charge on outside of the area. Those charge generate the field. Field comes here, but the charge are not. So this is setup I'm looking at. And in this region, because there's no charge, it's only E and B field, we can look at the Gauss law. Okay? The Gauss law tells me divergence of rho divergence of E should be charge density divided by epsilon 0. Sorry. Let me erase this. This is wrong. Okay. It's charge density divided by epsilon 0. Okay. Because in this area I have no charge. I purposely choose area where there's no charge. The rho is 0. Okay. Okay. So in this area, the divergence of E is 0. In this area, divergence of E is 0. If divergence of E is 0, we can immediately write down this relation. Okay? E dot divergence of phi. E dot divergence phi is something we want here. E dot divergence of phi. E dot of the curl. E dot of the gradient of phi. Sorry. E dot of the gradient of phi is actually as phi times E. Actually, the phi times E. Sorry, the dot product should be in front of the phi. Sorry for the typo. Okay, actually, let me erase everything. Okay, let me erase everything. Okay. So we can immediately prove this. E dot gradient of phi equals to divergence of phi times. Sorry, there is a small typo in my lecture notes. I should put the dot in front of phi. Okay. So this formula we can immediately prove. Okay. And the reason for that is, let's look at the right-hand side. Right-hand side is the divergence of phi times E. So phi is a scalar, E is a vector, phi times E is still a vector. Scalar times vector is a vector. Now for this vector, I can do divergence. Okay. And this guy, according to the derivative of multiplication of functions, we can immediately write down this as gradient of phi dot E plus phi E dot, divergence of E. Oops. Okay, this is what I want. Okay. So the divergence of phi times E is equals to divergence of phi, gradient of phi dot E plus phi times divergence of E. Okay, so this is nothing but a derivative for two functions that multiply together. We need to take a derivative for the first function and times the second function plus derivative to the second function times the first function. Okay, so that's a fundamental law of fundamental identity for derivatives. Okay. So the right-hand side equals to these two terms. Okay. As I mentioned to you earlier on, because I assume there is no charge density in my space, this guy equals 0. The divergence of E is charge density, which equals 0. That's Gauss law. Okay. because there's no charge in my space, this guy is 0. If this guy is 0, which means the second term disappears, okay? If the second term disappears, we proved that the right-hand side equals to the left-hand side, okay? So this equation does not hold generically, but it does hold when there is no charge in my space. Okay? So if there's no charge in my space, okay, I can rewrite this term into this formula, okay? So actually, let me massage this formula a little bit, because again, I put the dot in the wrong place. This guy should be divergence of phi times E. Okay? The dot should be in front. Sorry for that. My handwriting is really bad. Sorry for that. And this is a vector. Actually, let me erase this and to write a better formula here. Okay. It's a divergence of phi times electric field vector. Okay, that's slightly better. Okay. So that's the last term. Okay. And the last term here is a total derivative. It's a derivative of function. It's a total derivative. Now we can utilize what's that called? The Stokes theorem. Okay. Stokes theorem tells us if you have a total derivative. Okay. Let me delete this. Okay. So the bottom line is the last term is a total derivative. Okay. So if we the real quantity we want to get is Hamiltonian. Okay. And Hamiltonian is actually the spatial integral of Hamiltonian density. Sorry, there is no alpha prime here. There should be no alpha prime here. Hamiltonian is a spatial integral of Hamiltonian density. Okay? This curly H we calculated is Hamiltonian density, it's Hamiltonian per volume. And the total energy of my system is Hamiltonian density, energy density, integrate over the entire space. Okay? And if you do the integral over the entire space, this is the first two terms. The first two terms gives you this. Okay? And the last term gives you this. Again, I should put the dot in front of phi. Sorry for that, but it actually doesn't change any of our final conclusion. The most important thing I want to highlight for the last term is that this last term is the integral of a total derivative. Okay? For the integral of a total derivative, we know that we can use Stokes theorem to convert into a surface integral, Okay? So this is a surface term. So last term is a surface term. So if I have a system, and this is my system, okay? The last term only contributes to the surface. It tells us about the energy of my surface, okay? If I care about what happened inside my system, in the bulk, I want to say, no, the energy density here. The energy density here actually doesn't care about what happened on the surface, or it's the energy density on this point are not related with what happened on the surface. So the bottom line, the last term is there, but the last term is a surface term. If we want to know what happened inside my system, this term does not contribute because it's on the surface, it's not inside. Okay? So this last term, we throw it away when we look at the inside. Okay? That's the reason why, although there's a typo, it doesn't change any final conclusions in this part of the lecture notes. Okay? So at the end of the day, we can throw away this surface term because we are looking at the bulk inside the system. And that's the Hamiltonian relative to this. Okay? Hamiltonian is exactly this. This is a Hamiltonian of EM field. And if you recall what we learned in 505, we learned that the Hamiltonian density is exactly this guy. Okay? Exactly this guy. Okay? If we want the energy we find here, same as what we learned in 505, we have to choose this coefficient alpha prime to be 1. Okay? So this is another reason, and a more rigorous reason, why typically people choose alpha prime to be 1. Okay? Again, this value of alpha prime does not matter at all for equation motion. But if you want to measure, or if you want to give the energy of the B field, this alpha matters. Okay? When we choose this alpha prime value to be 1, the energy of the B field we get here match exactly what we learned in 505. That's why we should choose it to be 1. Okay, so that's the reason why alpha prime is chosen to be 1. Okay, so the bottom line, in this part of the calculation, in this part of the lecture, we showed that by looking at the action, let's say Lagrangian density, it not only tells us equation motion, it also tells us what is the energy carried by the system. And we get the energy by looking at the Hamiltonian. And we get the Hamiltonian by doing the Lagrangian, the Lagrange transformation from the Lagrange. Okay? And by comparing the energy we have here with the energy we learned in 505, we determine that this value of alpha prime has to be 1. Okay? So before we conclude today's lecture, I want to mention a couple points. Okay? First of all, in 505, we learned that the energy density or Hamiltonian density is E squared plus B squared. Okay, that's what we learned in 505. And remember, in this lecture, we learned Lagrangian density is the same thing, E squared minus B squared. Okay, so this first term is the same as the first term we have here. The second term is also the same as the second term we have here, except that we change the plus sign to minus sign. Okay, so that is what happened for E and M field. The energy and Lagrangian density are very, very similar to each other, except there is a minus sign for the second term. And this relation is very similar to classical mechanics. Recall in classical mechanics, Hamiltonian is kinetic energy plus potential energy. But Lagrangian is kinetic energy minus the potential energy. Okay, so in that sense, for E and B field, it has a very similar story. The first term stays the same. Second term also stays the same, but you flip the sign. Okay? That's a relation between energy and Lagrangian, energy density and Lagrangian density. Okay. Okay. So that's the first point I want to mention. And secondly, there's another point I want to mention here. Okay, because energy density and the Lagrangian density contain the same term, just a different sign. We can immediately know that these two quantities have the same unit. Okay, so this one is E squared, this one is E squared with the same coefficient, so they must have the same unit. Okay. For energy density, we know the unit is joule per meter cube, energy per volume. So this means immediately we know that the Lagrangian density has the same units as energy density. Its unit is also energy per volume. Okay, it's the same unit as energy density, so it's energy per volume. If Lagrangian density has a unit of energy per volume, then what is the unit of Lagrangian? Lagrangian is a special integral of Lagrangian density. Okay, so Lagrangian density has energy per volume as their unit. If you do a special integral, the special integral has a unit of volume. Volume times energy per volume gives you energy. So Lagrangian has the same unit as energy. That is again the same as classical mechanics. In classical mechanics, Lagrangian and energy, Hamiltonian, have the same unit, okay? Because they have the same term, just flip the sign. So in E and M field, in the field field, Hamiltonian, energy, and the Lagrangian also have the same unit. So Hamiltonian density and the Lagrangian density have the same unit. Hamiltonian energy and the Lagrangian have the same unit. Okay? So that's the energy of Lagrangian is still unit of Lagrangian is still energy, same as classical mechanics. Now, finally, how about action? Well, action is time integral of Lagrangian. Okay, we know time integral dt has unit of time, and Lagrangian has unit of energy. So action has a unit of time multiplied by energy. What is time multiplied by energy? Well, in quantum mechanics, we learned time multiplied by energy. This unit is nothing but the Planck constant, h or h bar. Okay, Planck constant has exactly unit of time times energy. So remember, we have the uncertainty relation for delta t and delta e equals h bar. That's uncertainty relation between energy and the time, which means h bar has a unit of time times energy. Okay? So in other words, action has the same unit as Planck constant. In other words, action divided by Planck constant. This guy is a dimensionless quantity. This guy has no unit. All the units perfectly cancel out. Okay? The denominator and numerator have the same unit, so all the units cancel out. This is the dimensionless quantity. And this fact is very important, okay? Because in quantum mechanics, we know there is a picture called the path integral picture. In path integral picture, we have different paths for the propagation or evolution of a particle, and different paths carry different weights. And that weight is this exponential factor. And in this exponential factor, action over h bar is a complex phase that we need to pick for this path. Okay? And complex phase must be dimensionless by definition. Okay, phase is a quantity. Phase is angle. Angle has no unit, so we have to use a dimensionless quantity to be this complex phase. And action over h bar is perfectly the right dimensionless quantity, and the same dimension as s and h bar, so they cancel each other. So this is the reason why s over h bar could be utilized as a phase factor in quantum mechanics. Okay, I think this is a good point to stop today's lecture. So in today's lecture, we did a couple things. Firstly, we start from the action and we derive the equation of motion and we find that's Maxwell's equation. And then we looked at this coefficients and we showed that this alpha prime coefficient should be 1, okay? Because it's simple and it's also because it makes the energy match what we learned in 505. Okay? And then we discussed about the unit of Lagrangian density, Lagrangian action, and we showed that action has the same unit and as the Planck constant. Okay, and today we will stop here, and the next time we will continue our discussion and look at what happened on the matter side. Okay, I'll see you next time.